Transition Matrices Part 1 Intro. This will be a 4-part series. Sometimes the best way to explain something is to just dive in with an example. So here I've said a taxi company called Uber runs a fleet of self-driving electric cars. The cars must recharge every night at either station A or station B. 85% of the cars that start at A return to A to charge, and 70% of the cars that start at B return to B to charge. So we have a station A. And then to make things simpler, we've got a B in blue. And let's have a look at our first sentence. We said 85% of the cars that start at A return to A to charge. So if we look at that, we're saying starting at A, returning to A is 85% of the cars. Well, 100% of the cars must exist, so the remaining percentage must be going to B, from A to B, and that's 15%. And we can see that all arrows out, total or sum to 100%. All right, and we can see that the same thing is going to happen when we look at B. So when we look at B, it says 70% of the cars that start at B return to B to charge. Well, let's draw that in. So 70% start at B and return to B, 70%. And well, what's left is 30%. So 30% must be going from B to A. And that is our rule that all the blue arrows add up to 100%, all the red arrows add up to 100%. And that's an important thing to remember. All right, now we can represent all of this. This is actually what is called a transition network. And you'll be doing networks and matrices together in the next unit as well. Networks or graphs is actually a graph, and the things you're thinking of with graphs are actually called plots. But we can represent all this data as a matrix. So let's draw a matrix. It's going to be a 2 by 2 because we're going to have A, and then B and B. Now, important thing to note here is that we're going from A to A. So this is your from part, and this is your to part. Another way to look at this is often, because we're talking about days here, you could be talking about this is today, and this is tomorrow. All right. Now this is different from communication and dominance matrices where you had the opposite direction. So just pay attention to that important detail. All right. Now, we don't do them as percentages. We're going to do these as decimals. So from A to A is 85%, which is 0.85. Let's make that a little bit neater. 85, and then from A to B is 0.15, and that totals to 1. All right, because that's the same rule as we have over here. So we said all arrows out total to 100%. So the columns must add it to 1. It's the same rule, just rewritten in different maths. So these columns total to 1. It's the same rule as that 100% rule, but just not done as a percentage. All right, there are no weird examples, well, there are in reality actual examples where they don't, but they don't seem to have done them in any past exam papers, so we don't have to worry about it. Not totaling to 1. Now, from B to B, now this is B to A, remember? So it's not the 70%, it's the 30%. So this is 0.3. This is the B to B, and that totals to 1. And just highlight another code word that will come up in some of the other examples. This diagonal here, which is the leading diagonal, you may remember from other videos, the leading diagonal represents no change. So that's A to A and B to B. So the leading diagonal what's gone there? Leading diagonal means no change. So please pay attention to whenever you see that as a code word, it says, oh, there has been no change. What does this represent? You go, oh, it represents no change if it's on the leading diagonal. And so this whole network here, this was our transition network, right? Well, this is called our transition matrix. And this dude is often called T for transition matrix. Fairly straightforward and fairly obvious. So there you go. All right, so we have our transition network and we have our transition matrix. I've just neatened that up a little bit. But now we need to talk about like, well, okay, I know percentages, but how many cars do I have? So let's have a look at that. So imagine we're just going to start with something simple. So we've got 100 cars at A, and we've got 100 cars at B. Well, that data we just put in there, that can also be represented by a matrix. So down the bottom here we have our matrix T, but now we're going to make another matrix of for the 100 cars thing, like so. This is going to be a 2 by 1. And so we say we've got 100 cars at A, and we've got 100 cars at B. Well, this is the initial state. So where we started, this is the initial state. All right, so this is S for state and 0 because initial, because you're just starting off. All right, now let's have a look a bit more at this in detail. So remember, this is our from, and this is our to side, right? And so we're going to multiply these things together, and that's going to give us another matrix. Don't need to go through the matrix multiplication right now, and I'll do it on a calculator later for you to show the calculator stuff. But this is a 115 for A, and this is going to be 85 for B. Another go at that writing. Now, this one is the next one. It says S1. Now, you can imagine, like, remember we said that this is from or to. We also said it could be thought of as today and tomorrow. It's hard to write that in. Tomorrow is represented by the transition matrix. So if S0 equals Monday, then S1 equals Tuesday, doesn't it? And that's why we can actually sort of talk about like a relationship, which is that S1 equals TS0. And this looks very much like compound interest because it is pretty much the same thing. And you're going to be doing similar maths with that. So here we have our S0 was Monday and S1 was Tuesday. Well, what about Wednesday? Well, Wednesday would be S2. So we said S1 equals TS0. Well, S2 equals TS1. And you might spot that this is our old friend recursion. So, you can imagine S3 equals TS2 and S4 equals TS3, etc., etc., etc. We'll get to that formula in a minute. But let's just show how to calculate this thing through and look at some important issues. So we're saying this dude is going to represent obviously Wednesday, so Monday to Tuesday to Wednesday. And if you actually pump these numbers in your calculator, you'll get 123.25 and 76.75. And you would be wrong. Why? Well, the problem is you can't have part of a car. So this is the rule. You must, this is another rule, must round to a whole number. Because you can't have part of the car. So this actually should equal, they asked you how many cars were in A, it's 123, and then B, doing the right colors, A and B would be 77. Notice that the total does equal 200, that does equal 200 cars again. All right, so we're starting to see some formulas develop here. So let's summarize some of our findings into formulas. So if we say that S1 equals T S0, S2 equals T S1, S3 equals T S2, etc., we can put this into a more general formula that Sn plus 1 equals T Sn. All right, but we can also do, I'm not going to derive it, we can also see that actually, just like we did with compound interest, I can just say like Sn equals T to the n S0. So these are our two important formulas. This one, which is for recursion. Now, what have I forgotten with recursion? You must always have an S0. So don't forget your S0 for that. Yeah, with our recursion, and then there's this formula. So if I wanted to find what's S5, what does that equal? Well, I could have done, you know, S4 equals T S3, S5 equals T S4, and I could actually have to do all that in recursion, or let's just make my 5 a bit neater there. We could just go T to the power 5 S0. Calculus stuff coming momentarily. And if I pump that into the calculator, I get some horrible decimals, but I'm going to round that off. I'm going to show you the rounding because I'm 3.6557, blah, blah, blah. And then I'll do it in blue, 68.3443, whatever. Can't have fractions of a car, round that off. I'm going to have S5. Now think about that. S0 was Monday, so S1 is Tuesday, S2 is Wednesday, S3 is Thursday, S4 is Friday, so S5 is Saturday. So if they asked you how many cars would be at A on Saturday, you would say 132. And how many cars on Saturday? So I'm going to put that, that's Saturday. How many cars would be at B? You would say 68, and we can still see that the total equals 200 cars. We haven't lost any cars, had any accidents, and that would be our answer. So you can see how this formula does work for us, just like compound interest. Okay, finally the calculator stuff. So not too hard so far. We can just take this matrix, and I'm going to put it in here. I'm going to label it T. And that's what I did, labeled it T, and that shoots it across there. And then I took this matrix, which is 100, 100, there. I labeled it S, not S0, because it's very hard to put the S0 in. Just call it S and put it in there. I typed in T times S. Just remember that, you know, when I'm doing it on my keyboard, it looks like a funny star thing. When you do it, it's going to look like a cross. And there's my 115 and 85, which perfectly matches that. So we can definitely say here that T S0 equals S1, because that's S1 right there. Now my answer for that one, which was this answer is this, right? So if I just do that, that's exactly the same as saying T times S1 equals S2, which is this dude that we said. And remember, they're going to give you the fractions, so you have to do a bit of work yourself and go, oh, that's 123 and 77. But that's what we got before, and that's how you do it. You can type the word ANS. That's all I did. I've got a keyboard. But if you can't be bothered using the recursion, and there's no compulsion to use the recursion, remember we said that you could have done, so the process was S1 equals T S0, so S2 equals then T S1, and that's the recursion way of getting S2. But you could have used the other formula, which is that S2 equals T squared S0. And that's exactly what I did in this one over here. So I just did that there, is that on the calculator, and you can see this numbers do actually equal the same as those numbers. So it definitely works. If you're finding S2, it's not that hard to put in the squared symbol. You can just remember, you can just alter it. You can click your pen in there and then, insert a hat 2 to get your answer as well. And again, I've just done a bit of recursion here. This part here is actually saying T times S2 equals S3, because this was T times S0, this was T times S1, so that's what we've just been doing. There's S1, there's S2, there's S3. Remember, don't forget to round off your numbers. Got a bit carried away here. This is S0, this is S1, this is S2, this is S3, this is S4. But you might notice actually that the differences, like to here, we've gone from 100 to 85, which is, minus 15. Then we've gone from 85 to here, which is 77, so we've dropped about minus 8. And then we've gone from 77 down to 72, which is minus 5. And then we've gone from 72 down to 70, which means we've only dropped 2. So we're actually starting to converge on a single value, okay? All right, let's go crazy and find out what, S25, and that equals T to the 25 S0. And I've tapped that onto the calculator here, and I got these values. Now pay attention to those values for the moment, and you can see there's not much change in there. And then I've changed that 25 to 26, pretty much the same values. So we can see that there's no real change in what's happening here. So we said that S25 equals T to the 25 S0, which equals basically 133 and 67. Again, total 200. And then we worked out S26, and we can say it's exactly the same thing as 133 and 67. So basically what's happened here is there is no change in the values, right? And this has a special name. This is steady state. And I would like to emphasize a special code word that they would say in the long term. All right, so if you see this phrase in the long term, they mean steady state, where you want to have a situation where there is no change. So we can say it doesn't matter if I was to work out S a million. I know S a million, S 1 1 2 3 4 5 6, it does equal 133 and 67. What would that mean if you're actually running a taxi company? Look, if I started, and remember this is A and B, if I had 133 cars here, and I had 87 cars here, that's the perfect setup. It won't change. At the end of every day, I'll still have the same number of cars at A and B. So when I want to put my resources out there, I want 133 cars at A and 87 cars at B, and I won't have any issues with running out of cars at A and having too many cars sitting around at B. So that's what we look for, that code phrase in the long term, and that's what we mean by steady state. And I'll show you one more weird thing about steady state, because this will help you with some exam questions. So we're going to say S infinity, that's steady state, equals, well, technically T to the infinity S0, but we can't do infinity on the calculator. It will take forever to do. All you've got to do is show that if, say, S25 equals S26, and some textbooks will say do 50 and 51, it doesn't matter, then you can say, then that basically is S infinity. So no change between S25 and S26, then you can say you've actually achieved steady state. Now, this is the interesting thing about steady state. So it doesn't matter what numbers you start with. So here I've done T to the power 25, and I've done a different starting state. So if I started with just if I just started with just like one car here, and I started with then the other 199 cars here, and I ran it for a certain period of time, I would still get the same numbers. Look, I've still got 133 and 67, exactly what I had. So it doesn't matter what numbers you start with. Steady state, it always converges on those same numbers. Look, we still got 133 and 67 there. So that's an important thing to note. We're trying to say that when you have S25 and S26 being the same, that's the same as S infinity, which is another name for steady state. And so when you were going to allocate your cars, you can start with 133 on A, 67 on B, but it doesn't actually matter what you start with. So one of the tricks they do on you on exam questions is not give you S0 and then ask you something about in the long term. Remember that phrase I was saying? So if you see that phrase in the long term, that's a very important phrase there, in the long term, then you'll know that it doesn't matter what your S0 is. Okay, a lot of theory, but this does tend to dominate the matrix part of the exams. So this is actually from last year's exam, and let's have a look at what they're asking us to do. All right, so we've got ourselves a transition matrix, lovely, but they've called it V just to be confusing, not T, thanks. And we've got a network diagram there. And so we want to find the value of X, which is over here, and what that is. All right, the problem is though, although we've got some lovely letters over here and here, we don't have any letters anywhere here. But can we work that out? Well, hopefully, because otherwise we can't get the question right. Now, if we look, we've got, what do we have that we know? Well, we can see there's a 0.4 here. Now, what's interesting about that 0.4 is there's only one 0.4 on the whole diagram. And that says we're going from this one to this one. Well, that tells us we're going from M to F. So that arrow is pointing from M to F. So we've already got M and F worked out. That's pretty cool, isn't it? And if this is M, and going out of it is this 0.1, well, that's this 0.1, and that's going from M to T. So if we follow the arrow, this must be T. And we don't know what the other letter is, except, well, it's only one place left, so that must be L. So now we've got all our vertices labeled. And the question is asking us about what's the value of X, and X is over here, and it's this loop around to itself. So that's from L to L. So from L to L, all right, well, that's 0.6 if you look in there. So the answer must be 0.6, which is C. X equals 0.6. A nice little bit of deduction there, just understanding the diagram. Okay, this is from the 2016 exam, and we've got a lovely diagram here. Now, the first thing that sort of strikes me is it doesn't look perfect. It's not everything's drawn. What we're missing is this arrow. So if that arrow doesn't exist, that must be 0%. So we know somewhere on our matrix we've got to have a 0. So this one does not have a 0 in it. This one does not have a 0 in it. This one doesn't have a 0 in it. So we've already got it down to B and E. How quick was that? So remember, every arrow must be there, and if an arrow is missing, it must be a 0%. All right, and we can double check all that because all the arrows out had 100%. So that's 60 plus 40, right? Well, that's 100%. So the only other arrow coming out is 0%. If you add all those up, you do get 100%. So that's why that arrow we had to draw in was 0. So, well, we could just focus on that 0. That 0 is C to T. So it's from C to T. It's from C to T. Boom. It must be B because that doesn't work on E. You can check out all the other values. They do work. I'm going to go slow just to annoy people. let's have a look at this. If we look at remember the ones going to themselves, like this, that's the leading diagonal, like that. But so H to H is 0.3. They're all got 0.3. T to T is 0.5. They've all got 0.5. And C to C is 0.6. So that only eliminated D. But you can check out all the individual values of all these things. It'll take a long, boring video. But the trick here was that 0. Okay, this is from 2017 exam 2. And it's part A and part B. So let's have a look at part A. It says, of the junior students who choose performance, P, what percentage are expected to choose S the next term? So if we go from P to S, we get, well, it's quite a simple number, isn't it? Isn't it just 40%? Now, you could draw up all the matrix and spend a lot of time on this, but you don't really need to. So it says 306 students are expected to choose S in term 2. So that's what we've got, this number over here of 306. And they're just asking you, how do you calculate that? So what they're saying is you've got a 300, a 240, and a 210. Well, it's quite likely that that's going to represent P, S, and T. So if we're starting at P, and we're trying to go to, remember, we're trying to go to S because it said that was what we're doing. We got S was 306. We highlight that value. So it's P times the S there. So that's times. Now, don't remember, we've got to put this as a decimal. So it's 300 times 0.4 because that's the 40%. All right. And then if we look at the next one, S going to S. So that's S going to S is our next value. So S going to S is 0.6 because that's what 60% represents. And the next one is the T's that become S, all right? So the T's that become S, so from T to S here is 20%, which we write as 0.2. So if you do actually check that on your calculator, and what I love about this question is, if you get the 0.4, the 0.6, and the 0.2 wrong, one of them wrong, it won't equal 306. You've got a self-checking question. If you don't get 306 with your values of 0.4, 0.6, and 0.2, then you've made a mistake and try again. Okay? But what they're basically saying is, if you want to get S this time, then you've got to consider all the things that go into S, all right, for the next time. So we've got to consider P to S, S to S, and T to S, and that's where we got our 3 values from. But I love that because it's a self-checking question, and it's 3 marks. Wow, easy peasy. I forgot about part C, but this is a ridiculously easy mark. So we had 300 people here, yes? We had 240 people here, and we had 210 people here. That gives me a total of 750. It says in term 4, but we don't need to worry about that. It says how many students are expected to participate in total. Well, 750. We haven't created or destroyed students. If I read from the examiner's report, it says this question did not require any working if students realized that the original population of 750 remained unchanged throughout the transition process. Now, some people did use a transition matrix to represent this, so terrible terminology here. So S1, which is term 1, we use S for term, is T S naught, and then you got S2 equals TS1. And so let me just label that. That's term 1, that's term 2, this is term 3, and this, so term 4 would be TS2. This actually would be term 4. People ended up with all like rounding errors and stuff. They did a big transition matrix. They got they got all this and put it in to make a T, and then they worked it all out, and then they rounded off and found they'd lost a student somehow in the rounding and got 749. But the question was, like, how many students in total? Well, you haven't lost any students. They're all there at the end of the year, you hope. 'Tis the dream.